Okay, I'm very happy to kick off the reading group meeting for this quarter, and hopefully we can learn something through the two papers that I will share with you today. So the first paper is about GIT, the Generative Model of Generative Image-to-text Transformer for the vision language. So this is a recent paper on the archive from Microsoft. Yeah, so firstly, just a very basic description about the multimodal task or the vision language task. So as we have been known, so there have been multiple different vision language tasks like the image captioning, the VQA, visual question answering, and also the visual entailment. So all of these are actually based on the idea that how can we jointly learn the semantic information or representations from different modalities, for example, from the vision, the image, and the text. So this has been the key problem for the multimodal representations that I will introduce today. So firstly, I will give some basic idea about the key point for this work. So what's the motivation that they propose this kind of the new model or new methodology? So firstly, the motivation is to unify the different model tasks. Sorry, there are some people in the waiting.
Yes, you should be able to hit accept. I was trying to do it, but I can't.
Okay. Oh, sorry. Yeah. So this model is trying to unify the different vision and language tasks. So including like, for example, the image captioning, the image VQA. So if we have the question, how could we deal with the answering? And for the video, so if we have multiple frames of the images from the video, how can we do the captioning for the video? How can we do the VQA for the whole video? So how if we could come up with a single model or unified model that could deal with this kind of different vision language tasks? So this is the first motivation for this paper. And the second one is about the model structure. So if we look at the current or existing works on the vision language task, so there are actually different model structures that has been introduced for the different tasks. So for example, there are unimodal encoder, the multimodal encoder, and also the fusion decoder. So there are different kind of the different attention mechanisms, the different framework to jointly learn the representation from the image and text. And some of them are also depend on the object detector. So for example, how can we extract the bounding boxes or the regions from the images that can be related to some specific words in the semantics? And for the pre-training task, so this kind of models always have the different tasks that have been introduced. For example, the mask language modeling. So if we mask some tokens in the sentence, how could we predict the tokens based on the reasoning across the other text tokens and also the image tokens, and also the image text contrastive learning and also the image text matching. So these are many different kinds of the constraints or the loss function as the pre-training task that is help us to learn the vision language modeling. So in this work, which is introduced as a GIT model, so they're trying to simplify this model structure that can be proposed to deal with the different vision language tasks by using only a single image encoder and a single text decoder. And also more interesting is that they only use a unified pre-training task with the language modeling task, which I will introduce more in detail later, and exclude and also ignore the different loss function or different other pre-training tasks, and can also still achieve pretty good results. So this has been the second motivation for the simplified model structure. And third one, in the third dimension of this work, is try to scale up the pre-training data scales and also the model size in order to boost the model performance. So for example, in the paper, it has introduced do the application study for this kind of different 3 different pre-training data scales and also 3 different model size. So as shown in this table, and absolutely when the training data size and also the model size has been scaled up, the model performance can also be boosted to some extent. So this has been the third effort that they propose this method for. So, okay, so based on this kind of 3 key points or motivation, so how we could achieve this. So what kind of the methodology they proposed specifically to also achieve the state of the art in the different vision language tasks. So getting to more in the technical details for the GIT model, the key point here is that we want to use this kind of single image encoder and a single text encoder by concatenating the image features and the text embeddings. So if you look at this feature for the left or bottom part, so there is an image encoder which is pre-training on some contrastive learning task. So by using this pre-trained image encoder, we can extract the image features from the entire image, and which will be fed as the input for the text decoder. So by going through the one layer of the image feature projection, so these image features will be concatenated with the text embeddings. So for the text input, we do the tokenization as a standard process and do the text embedding. And then the image features and the text embedded are concatenated with some special tokenizers and tokens like the beginning of the sentence as the input for the text decoder. The text decoder is a transformer-based model, which is randomly initialized. And the output for this kind of text decoder is trying to generate the sentence or the text in an autoregressive way. So this is how they do this kind of the language prediction. And through this way, they're trying to reason across both the image features out from the image encoder and also the text embedding through this kind of the multimodal fusion way, and then trying to predict or output the sentence, which is actually the target here. So this is the pre-training task. And as we can see, here, a very important thing is that how we can do the reasoning by reason across or both the image features and the text features. So in order to do this way, they introduce this kind of the self-attention mask. So we can see that here on the right figure, this is a sequential to sequential attention mask, where for each point ij, which means that the I output can be attended to the j input related. So this which means that for all the image tokens, they can attend to each other through this kind of the transformer-based model. But for all the text tokens, because we want to generate the text as the output in this kind of the autoregressive way. So the prediction of the text token will be depend on all the image features as well as all the left side tokens. So this is the reason why they could learn this kind of the reasoning across the multimodality. And with this kind of the self-attention mask also as the input to the text decoder, we can predict the text or the language as our output. And for the pre-training task in this kind of the also as a self-supervised learning objective, the target is to compare the predicted text tokens compared with the ground truth here. So that is the language modeling loss here. So we can see this kind of loss is pretty straightforward because it predicts all the text tokens in the language as the input. But why they did not use the mask language loss here, like what the other paper is doing? So the mask language loss is trying to mask some text tokens and only predict the mask text tokens from the corrupted input. So that's has also been introduced in many previous works. So this paper has introduced this language modeling loss because they think this kind of language modeling loss could be more efficient in the computation. So for example, if you mask like for every iteration, like 15% of the mask loss, and you will need to run more epochs or iterations to achieve the equivalent performance, equivalent stage compared with the language modeling loss, because every time you only predict the tokens that are masked. And the other way to do this, so this is the reason that why this paper proposed the language modeling loss, because for the large scale training, this could be more efficient, especially within the limited epochs. So this is how the model do the pre-training with the language modeling loss and also this kind of unified and also simplified model structure. And then after the fine tuning, we will see that how this model can be used for the different downstream tasks, like we just mentioned, for image, video, and captioning, and also VQA. So firstly, for the VQA, here we need to think about how can we concatenate the prefix, the question. So that's also kind of straightforward by using this kind of unified model. So here, they concatenate the question and also the answer. So concatenate two sentences together as the input for the text decoder. And then in the output, with the self-attention mask, they only predict the answer, the sentence for the answer, and they only compute this kind of the loss language, loss modeling loss for the predicted answers. So which means that with the context of the image and also the prefix from the question, so we want to do this kind of reasoning through the text decoder and to get our answer from both inputs, from this kind of input information. So that is the way that how they do the VQA task for both the image and the video. And later on, how they could deal with the video task. So this is also kind of the straightforward way by doing this kind of the different embedding for the different frames. So which means that when giving a video, they extract the different or multiple frames as the different images, and then going through the image encoder separately, the features of the multi-frames can be extracted. And then by concatenate this kind of the features, they could get this as a video representations, which is used for the input for the text decoder. So that is the way that this model is used for the video tasks. And now later I will share some numerical results for the different experimental on the image and the video captioning and the VQA. So firstly, this is the results for the image captioning and on the different benchmarks. The matrix is used here is for the CIDR scores. And we can see that the GIT can achieve pretty comparable results on the different benchmarks compared with the previous state of art. And also one important thing, interesting thing to note here is the results on the text caps. So you can see that in the subtable E, for the text caps, so this paper claims that for the first attempt, they can get the better results compared with the human performance on this data set. So there are some qualitative results for this data set, which is actually can do the captioning from not only just a simple or pure image, but also some images with like the logos, the titles, and also the logos. So this is the first time it can surpass the human performance on this specific benchmark for the image captioning task. And absolutely, there are also some other tasks for, like, for example, like the image VQA, use the methodology that we introduced earlier by using the question embedding as the prefix for the generation, and also the video captioning by concatenate the features from the different frames as the video representations and also the video VQA. So I will not go through all the numbers in detail here, but you can always refer to the paper for more details. So it has really done pretty intensive experiments for the different tasks and also compare with the state-of-the-art results. And also some other interesting thing to see here is for the evaluation study on the scale-up experiments. So like we mentioned earlier, so one interesting thing is paper is that it tried to scale up both the pre-training image data scale and also the model size. So here it showed the evaluation study of the 3 different model size and also the 3 different pre-training data scales on the different benchmarks, including the image captioning and also image and also the VQA task. So we can see that how the pre-training data and also the model size can further boost the model performance in this kind of vision language task. So just to give a quick summary about this paper, so it has been this kind of interesting point that this kind of points that I feel interesting. So firstly, try to unify the different vision language tasks through a single model, and then it tried to simplify the model structures. So by excluding the different pre-training tasks and loss function and also the different model structures, it used this kind of the single image encoder and the single text encoder can be very strong in the model performance, but also can be very generalizable for the different tasks, different downstream applications. And the third one is that they try to scale up the pre-training data scale and also model size to further boost the performance. So after we read this paper, we see that how they could achieve this kind of the different thing. The key point here actually is the concatenation of the image features and also text embeddings as the input for the text decoder. So this actually can be very interesting because here we were trying to fuse the information from the image and the text in the feature space or in the embedding space. So we could ask this kind of question. So if we could concatenate like different modalities of the data in an early stage fusion, so even before the feature learning or embedding learning. So later on, I will also briefly introduce the other paper that I feel kind of relevant to this work, and also in some perspective, and also have shared some similarity and overlaps. So this paper is called the BIT 3. So this is also a pretty recent paper on arXiv and also from the Microsoft to solve the vision language task. So firstly, as we just saying that, so beyond to just concatenate the image features and also text embedding in the embedding space. So actually what we could do is to think further stage, which means that we concatenate the embedding from the image patch and also the text tokens, even at the input. So the key point for the BIT 3 model is to try to regard or consider the image patch or consider the image as some kind of the foreign language. So after the image patch, after the tokenization, we just think image as one parallel sentence as the language or as the text input, and then use this in a unified manner for the training or the reasoning across the vision and also the language modalities. So this kind of model is based on this general purpose multimodal foundation model. And the key point here is that for the different modality input, like the image and also the text, it has this kind of the modality specific encoding and also have the cross-modal fusion in the upper layers. So we will introduce in detail how they achieve this. Specifically, they introduced this kind of the way, this kind of the architecture called the multi-way transformer. So the multi-way transformer, which is a pretty general purpose for the process or the learning through the different modalities, including either single image, single modality, single text, or the image text pairs. So the key point here is that for the first part of the self-attention layer, it has the shared part of the self-attention module. But for the later part in the feed-forward networks, it builds this kind of the different experts for the different modalities. So this kind of the shared self-attention module can help to further node alignment through the different modalities. And then through this kind of modality-specific encoding and also the vision language expert, it can further nerd the interactions between the different modalities in a deeper way. So this is the key point or the key modules for this model, how they could include the image as some foreign language to process the data, multimodality data simultaneously. So specifically, how they train this kind of model. So if we think about the image patch or as the text token as well, so actually this can unify the manner for the pre-training task as well. So what they do is a unified masked data modeling. So which means that no matter if we input this the single modality or the multimodality, like the image text pairs, we just mask the tokens. This can be image patches, this can be text tokens, and then try to predict the mask tokens based on the corrupted input sequence of the tokens. So that's the key idea or the self-supervised objective in this pre-training model. And then later on in this kind of the fusion encoder, which is showing in the subfigure C. So they try to jointly encode the image text pairs, but in the interaction, not only from the input layers, which is for the vision and also the language experts, but also in the top 3 layers, they have this kind of the vision language feed-forward network that should even further jointly learn the representations through the different modalities, and by predicting the mask tokens, either in the image or in the text tokens. So this is the key ideas how this model can be used for the vision language task. And also, as we mentioned, since here we regard the image just as another language. So this model can also be used for owning the vision tasks or use the owning as a language task. So that is also the reason why this model can be used for both vision and also multimodality applications. So this is the key ideas for this BIT3 model, that by concatenate or by fuse information of the image and the text in an earlier stage, and especially by regarding the image as another kind of the foreign language, so we can use the unified manner to deal with the different modalities in a unified way. And if we think about from the other thing that we just introduced, that we have seen from the first paper, it also have this kind of the similar behavior or motivations. So firstly, this paper is also trying to propose the model that can unify the vision tasks and also the vision language tasks. So as shown in the right figure, so in this kind of the different vision tasks, including the classification, the object detection, and also the semantic segmentation. So there have been state-of-the-art by using the different task-specific or domain-specific network of model to achieve the state-of-the-art model. But this work can achieve both the pretty comparable and good performance on different vision tasks and also for different vision language tasks as well, because of this kind of the multi-way transformer for the modality fusion. And for the second thing, it also trying to simplify the model structure. So firstly, based on the specific module that with the multi-way transformer, it can unify the manners to process or to learn this kind of the image and also the language features. And in this way, because of this kind of the unified module, so it can have the pre-training task in a unified way by mask data modeling. So no matter if it is an image patch or text token, it can use this kind of the mask and then predict task to learn the representation or the fusion across the different modality of the data. And the third thing in this paper, they're also trying to scale up the pre-training data and also to scale up the model size, but it haven't done the evaluation study across the different data points. But this have been showing to include many different sources of the public data sets to train this network through the pre-training. So this is the key point I want to show with this BIT3 paper. And finally, it also achieved a new state of the art on the different vision tasks and also the vision and the language task. You can refer to the paper for more details in the experiment results. And then finally, just a quick takeaway. So through the paper introduced today, I want to share with you this kind of the convergence for the current works in the vision language modeling or the multimodal representation learning. So they use the how they could unify the different vision language tasks, how they could simplify the model structure, and also how they scale up the pre-training data size and also the model size to further boost the model performance. And in this share presentation, I share this kind of the two new ideas or new papers by concatenate to the image features with the text features, or to regard the image as one kind of the language, and then fuse information in the tokenized or in the image and also the text tokens. I think there are also more interesting works like the COCA, the OFA, which is following this kind of the convergence in this field. That is very interesting, but we're also very interested to see how this can be used for the radiology reports generation in the domain specific that we're interested in. Yeah, so thank you so much. That is what I want to share in today.
All righty, thanks, Shirley.